So thank you all. It's a pleasure speaking to all of you. So the title of my talk is Crouching Harm and Hidden Bias, Addressing Issues of Fairness and Bias in AI/ML-based Decision-Making. I'm pleased by the fact that a couple of speakers before me have already touched upon the issues of fairness and bias, Dan and Leah. So I would be covering a little more details of what is happening today in these areas and how can we prepare our organizations to address the various regulatory frameworks. So a short intro about myself. I'm in the Boston area for over 25 years, technical leadership, architect roles, large companies as well as startups, and have worked in finance, edtech, utilities industries. I've built cloud-native high-performance frameworks and applications, as well as architected modern data and analytics tech stacks. Right now, presently, I am Chief Data Officer and Head of Data Practice at EQengineered, which is a consulting company based out of New England. All right, so the outline of my talk has these broad themes. So we'll first cover the concerns of fairness and bias in AI/ML-based decision-making, how biases can get introduced, what are some examples of real-life bias. Then I'll touch briefly upon on the evolving regulatory frameworks for bias and fairness, and then spend some time on discussing how we can build compliance with these frameworks. Now, we all know, and some of these talks have already touched upon, that AI/ML-based decisions are rapidly being utilized by almost all companies, both here and internationally, both private and public. But this is a rapidly evolving field, and we have much to learn, and we may not really know what impact our decisions will have on actual humans. So as this slide shows, these are links to two separate recent surveys, one from PricewaterhouseCoopers, another from Gartner. As I mentioned, this adoption of AI is increasing very quickly across multiple industries and both public and private sector. And these decisions impact all of us. So here are a few examples commonly discussed in the news. For example, in the criminal justice, there is a tool called Compass, and there's another called Predpol, which the Compass actually tries to identify if a defendant is likely to commit more crimes if released. Similarly, fraud prevention is widely used in credit card processing to identify if a credit card is stolen. Credit risk evaluation to identify if a borrower is likely to default. And similarly, in preventive healthcare, from some test data, if we could predict if a person is likely to develop a particular disease. Similarly, for university admissions and recruitment, ML-based decision makings are widely being adopted. Now, what is often forgotten, that in many of these cases, these tools that are being used are biased against certain population groups, or they cannot handle situations which they did not get trained for. So their training data is different from the real world data. So in production, their decisions may have biases. And increasing attention of government regulators across the world is now going towards these systems so that these unfairness and biases are addressed. Now, first, let me talk a little about what exactly is meant by bias, because this term may be used with slightly different meanings in machine learning and statistics. What we are going to talk about, the issue of fairness and bias, The dictionary definition is, of course, a tendency to believe that some people or ideas are better or worse than others. In the algorithmic context, it means that systematic and repeatable errors in an algorithm can create unfair outcomes. And in certain cases, it can further marginalize already groups who are already at a disadvantage in some ways or other. So at this very fundamental level, addressing algorithmic bias is really a question of how we can support societal values of fairness to ensure that these decisions do not create discriminations or unjust impacts. Now, I want to distinguish between another concept, which is also termed bias in statistics and machine learning, that of statistical bias, because this is often confused by many. And this is purely a statistical measure, often coupled with the other concept of variance, which tries to measure, estimate a model's errors. Now, a model may summarize real-world data correctly with reduced statistical bias, however, mirroring real-world biases. So even if we say statistically my model, we have been able to reduce statistical bias, it does not mean it's still fair. So that's an important distinction I wish to make at the early in the talk. Now, what makes this whole field complex, and I will see some other examples of complexity, that bias or fairness is often depends on the beholder. So here, for example, from the decision maker's perspective, and in the field of criminal justice, it could mean that of those labeled high risk, how many will recidivate or basically commit another crime? From the perspective of the defendant, fairness could mean, am I being incorrectly classified as high risk, basically a false positive from these models? From the societal perspective, there could be two mutually conflicting definitions of fairness. Is this set of high risk classifications demographically unfair? Or will implementation of a fairer release policy could cause crime to go up? So as I mentioned, this is complex and there is no standard definition of bias, and we are essentially going to have to muddle our way through to these very complex questions. There is a link to an YouTube video at the bottom of the slide, which discusses 21 fairness definitions and their politics, which is very instructive. Now, there is a whole lot of work going on for bias. This is just a representative picture from this website. As you can see, we have areas for understanding how bias happens, how can we mitigate it, how can we account for it, and then there's separate legal and compliance related work that is going on in this space. So let me now briefly touch upon what are the various sources and categories of bias. So we see a very simplistic machine learning pipeline here. So the first 5 boxes under the stage marked as data essentially start from data acquisition to labeling to various pre-processing to make it ready for consumption by a model. So under the data processing phase, here are a few categories of biases. Historical bias is already existing bias because society, be it here in the US or anywhere else in the world, already has certain biases regarding certain subgroups of people. And the data may reflect that kind of bias. So even if we do perfect sampling, some groups of people may be unfairly biased. So training a model on this historical bias will produce biased results. Representation bias essentially is if a particular subgroup is underrepresented or overrepresented, typically say gender-based representation or race-based representation could cause biases in the decision-making. Annotation or labeling bias occurs when either through automated labeling or human labeling, because they could carry over certain biases in the existing data as well as in our decision process. So, I'll show later how human labelers could add their own biases to labeling. The measurement bias occurs when we choose certain specific variables which may not reflect real world data. So essentially, this is a proxy for certain target variables like, say, creditworthiness, or is somebody a good employee. These do not have any analog of real world data. This is simply a made up construct. And in making up this construct, our biases may be propagated. As part of the model phase, I have listed here 4 categories of bias. Selection bias may be caused by the choice of the classifier or the hyperparameters. Different models may have different generalization characteristics. So let's say a random forest or SVM or XGBoost could aggregate underrepresented groups in different ways. Aggregation bias occurs when distinct populations are inappropriately combined. For example, if we have 2 subgroups of people, for example, male and female, and we are trying to predict heights, if we combine these 2 groups of people, obviously the prediction will be incorrect. Evaluation bias occurs when the model is trained with data which is different from the data it will face in the real world. So, so obviously its predictions will be biased in some way. Optimization bias is an interesting one because the prevalent idea is, and what we have seen so far in my talk, is most of the bias is data related, but in certain cases, biases may be introduced even by the model, particularly in deep neural network models. Optimization techniques like compression or pruning could also introduce biases in underrepresented groups. The last phase, which I've shown here, is the interpretation. The model is working and it obviously spits out a decision. And here we could have a bias of the interpretation where a human reviewer could override a model's decision with their own biases. And the opposite effect is when an automated tool overrides a human's decision. So in either case, there could be biases in the process. So here are a few examples of algorithmic bias. Many of them are well known. So under historical bias, word embeddings trained on Google News articles. So this paper points out how it persists in making some gender-specific biases. Man is to computer programmer as woman is to homemaker. Representation bias in recruitment. So there was this tool developed by Amazon a few years back, which tried to predict who would be a good employer from analyzing resumes of successful employees. I misspoke. I said who would be a good employee. And it ended up discriminating against women candidates. To Amazon's credit, when they identified this problem, they retired this tool. Annotation or labeling biases. There are these 2 papers I've pointed out here. The first one shows how human labelers can introduce their own biases. And the second one shows how 10 publicly available data sets have almost up to 5% of labeling biases. Under measurement bias, this is the famous case of the tool called Compass, widely used in police departments in the country, which unfairly targets Black defendants over white defendants for the same crimes. Under aggregation bias, this paper points out inappropriately combining ethnic subgroups to predict chances of diabetes occurring could bias against some groups of people because the level of A1C may not be same across multiple subgroups. Under optimization bias, as I mentioned earlier, these three papers point out how deep neural network compressions and pruning could introduce their own biases. Now, as we have seen, because of these increasing pervasiveness of these machine learning tools and techniques in decision-making, regulators across the world are waking up to the risks of these situations. And today, about 60 countries have developed or are developing AI policies. And important thing about these policies is, for example, if we take European Union policies that are currently in draft mode, they have extraterritorial reach. Just like GDPR, it does not protect a company in the US if an EU citizen is impacted by the decision it makes. And it carries heavy penalties, sometimes up to millions of euros, so that organizations have to be prepared for such regulatory frameworks as they go on building their AI/ML-based decision tools. There are self-regulatory efforts from the industry as they recognize that regulation is coming. So I have listed a few here from Microsoft, Google, Amazon, Facebook, Apple, all the big names. But as we have seen from our experience during the 2008 financial crisis, self-regulation does not always work. So government regulatory frameworks are coming, and we have to be prepared for it. So how do we prepare for these frameworks? So although there are, as I mentioned, 60 separate countries are building this framework, there are some clear commonalities across those frameworks. So some of them are listed here. So they require these companies to perform what is known as an algorithmic impact assessment, also known as IA for AI or conformity assessment, which requires the company to conduct assessment of risks and identify unintended outcomes or sources of risks. It also requires separate audit. So in most cases, the group developing these machine learning models, the data scientists, the machine learning engineer, the data engineers, do not have domain expertise, and they do not understand how their decision could impact actual humans. So it is required that these models and their decisions are reviewed by people outside that core development group, and in certain cases, even external audit may have to be performed to identify these risks. And the third point is, as Leah had mentioned earlier on her talk on AML, that data and models drift with time. The data changes, the environment you're working on changes, and the model may, even if it is bias-free today, may not be so after time passes. So regulators are increasingly needing that risk management become a continual process where these decisions are being continually reviewed, and if required, the models need to be retrained, which also means ML ops is no longer optional. We have to put in a continuous ML lifecycle process in place, somewhat like DevOps has become mainstream today for most software development. ML ops have to become mainstream so that models can be quickly deployed, retrained, and rolled back if necessary. So here are a few high-level approaches to algorithmic bias mitigation, going from left to right. So as I mentioned, the impact assessment, we identify possible adverse outcomes of the algorithm early. We have to know the provenance of the data, understand where the data is coming from, if certain groups are under or overrepresented. Most publicly available data sets, as I had mentioned earlier, have some biases in them, so we have to be careful where we get the data from. Auditing for bias, we have to do regular reviews of the data and the decisions to identify and address bias. We have to continually monitor and train these models. We have to partner with experts. The people developing the models may not understand the implications of their decisions, so you have partners with users, domain, legal, and risk experts, and also civil society organizations like NGOs who understand the reality on the ground and understand how these biases can carry over to real life impacts. Aiming for transparency, this is in particular in regards with proprietary ML tools. Today, most proprietary ML tools for commercially available, they do not provide us with any visibility in how their decisions are taken. So it is important we ask these questions with these vendors. Prioritize interpretability or explainability. When we are developing these ML models in-house, we have to make sure we invest in tools and techniques to improve their explainability so that we can explain to the end users why certain decisions are being taken. This is obviously also evolving. There are no standard ways of explaining decisions work. So there is something that we have to make sure we try our best to build. And then incorporating human oversight, making sure that particularly in critical situations, ML decisions are have a human moderator overseeing the decisions. So a few templates, I will not going to read through it. So algorithmic impact assessment, as I mentioned earlier, basically asks these questions under these various categories, trying to identify who the audience will be, who will be the most affected by it, how the bias detection will happen, how we'll engage stakeholders, groups, and what kind of incentives are to be is there to develop this model. I provided links for each of the slides that you can go to those papers to learn more about these efforts. There are several frameworks and tools that are being proposed to document data sets and models. Here are 4 links. So as examples, there is this template called Data Sheets for Data Sets, which tries to document the provenance of the data, how it was composed of, collected, how was the labeling done, how has it been cleaned, what use it has been put to, and how it is being distributed and maintained. So there is also a proposal for documenting models using this model card template. So basically decisions you have taken to develop a model, the intended use, what ethical consideration there may be for the application of these models. So here are 2 example model cards from this paper. On the left, we have toxicity in text, and on the right, we have smile detection in images. And you can see it clearly tries to identify the ethical considerations and caveats and recommendations for these particular efforts. And increasingly, many of the mainstream machine learning conferences are requiring that you provide these model cards along with your paper. This is a template for suppliers to force them to document how their models have been trained, what are the sources, if possible, they tested for bias and things like that. And for learning more, there are a few tools and resources for bias mitigation. So on the first three, we have actually executable tools which can scan your data and identify over and up, underrepresented groups. The fourth one is an online course to make you more familiar with these various issues of fairness. And the last one, responsible machine learning principle, from where I have taken this slide, essentially is like a Hippocratic oath for data science practitioners to kind of commit ourselves to do the best thing so that we do not unfairly impact people. So I will try to end this talk with this message that we should not be, as data science practitioners, content with saying that we are simply building a technology, because this has real life impact on diverse groups of people. Some of them may be already marginalized. And we have to recognize these toolbox of AI and ML-based techniques is at best a flawed and somewhat immature collection of techniques, which is being obviously improving. But today, it is not such a state that bias and fairness can be guaranteed. So we cannot treat it as a black box and hand wave our way out of it, saying the machine is taking these decisions. So we have to try our best to make sure that the decision should be as unbiased as possible, and we should be ready to correct if these biases are identified.